Welcome back to the Mechanics of Solids lecture series. We're solving for shear and bending moment diagrams. In this video, we're going to conclude the example that we started in the last video. Note that I've recorded my reactions, 11 kilonewtons at support A, 51 kilonewtons at support B. I've also extended my lines down for the shear and moment diagram, indicating all the load discontinuities, the places where the diagram is going to change. And I've created an axis for the shear diagram, labeled it with kilonewtons, an axis for the moment diagram, labeled it with kilonewton meters. So let's start by drawing the shear diagram, working from left to right. Starting at point A, we cross the reaction, 11 kilonewtons pointing upward. So the diagram jumps up by 11 kilonewtons. Between A and B, we have a distributed load pointing downwards, so shear is going to decrease. Because the distributed load is uniform, the shear is going to decrease linearly, and we can calculate the value at point B as the value at point A minus the area under the distributed load diagram, which would be 4 times the length 8. I guess there's no diagram there, but it's the area under the distributed load. This calculates to minus 21. So I draw this something like that, and the value right here, 21. And I prefer that you just keep a little running tab of your calculations out to the side. You don't have to include units, just keep track of your calculations. When you reach point B, we have the reaction 51 kilonewtons pointing up, so the shear diagram is going to jump up by 51 kilonewtons. Negative 21 plus 51 equals 30, so it jumps up to 30. And then between B and C, there's no load acting, so the shear is going to be constant. Extend a straight line. And then when we reach point C, we have the 30 kilonewton load pointing downward, so it's going to jump down by 30. And in fact, 30 minus 30 equals 0. And so we confirmed that the diagram returns to 0 at the end, which is always an important thing to do. Okay, let me label the positive and negative regions of the diagram. Now we can solve for the moment diagram. Again, working from left to right, starting at point A. This is a pin support, so the moment at A is going to be 0. So looking at the shear diagram is linear, so we know the moment is going to be quadratic over this region. And the moment where the shear is positive, moment's going to increase. Where the shear is negative, moment's going to decrease. And where the shear is 0, the moment's going to reach a local maximum. It's going to look something like that. Okay, we need to find exactly where that occurs. I'll label that x. We can calculate x. This is the quick and easy way to do it. It's the value of the shear, 11, divided by the slope, which is 4. So that gives us 2.75. So now the value of the moment diagram at the location where it reaches its maximum, which is an important thing for you to solve for, because you want to know the max moment anywhere on the beam. We would calculate that as the area under this shear force diagram, 1/2 times 11 times 2.75, which calculates to 15.125. So I'll label that 15.125. Okay, now I know the diagram is going to having reached its max, is going to come down here and some value. Let's calculate that value as the value at the max, 15.125, minus the area of this triangle, which would be 1/2 times 21, its value at the end, times the length, which is going to be 8 meters minus 2.75, or 5.25 meters, which is negative 40. So this comes down here to negative 40. Sorry, I usually just put the values. This is positive and this is negative. Now we reach a concentrated moment, 80 kilonewtons acting in the counterclockwise direction. That causes the diagram to jump down by 80 kilonewtons. So negative 40 minus 80 is negative 120, be 120 down here. And then over the last part of the beam, the shear is constant, so the moment diagram is going to be linear. It's positive, so the moment diagram is going to increase. And we expect the moment to come back to 0. Let's check. Negative 120 plus the area under the shear diagram, 30 times 4, indeed is equal to 0. And I will just draw this as a straight line that comes back to 0. And that's the conclusion.